So in the school, we not only have talks around the projects, but we also have single invited talks. So Yuzaburo, Nakano, I hope I pronounced it correctly,
exactly,
is going to talk about elephant random walks, but from a certain perspective.
Yeah.
Of course.
Thank you for the introduction. And my name is Yuzaburo Nakano, and I'm a first-year PhD student at Yokohama National University. First of all, I would like to thank the organizers for a kind invitation to speak at this workshop. And today, I will talk about two topics. And one is elephant random walks with polynomially decaying steps, which is based on the published paper last year. And the second one is on the Takagi-van representative functions via elephant random walks, remembering the very recent past. And this paper, this is based on published paper in this year. And the second one is based on, is partly joint work with Professor Takagi.
Can everybody understand? I think it's okay. Yeah, okay, good.
Can you hear me?
Yeah,
okay.
I think it's okay.
Online, ask, speak up.
They ask the ones online whether they can hear you.
Can you hear you? Online audience. Ask, ask me.
You ask them.
You ask, okay.
Otherwise, I think they would have already protested. Okay, please go ahead.
To motivate the discussion, we first introduced a classical problem, which is called random signs problem. We first 1 over k and sum over k from 1 and infinity, and this series has diverges. But we alternating sign as it is alternating plus minus 1 sign, and this series converges. And then randomize this harmonic series signs with RK, IID random variables with plus minus 1 is equal probability. Then this random harmonic series converges with probability 1. More generally, for sequence AK, the question is, does this sigma n, AK, RK sum over k, 1 to n, converges or diverges? And this sigma n obeys the following statement. If AK is not square summable, then sigma n diverges almost surely, and oscillating minus infinity to plus infinity. On the other hand, if AK is square summable, then sigma n converges to some finite real number with probability 1. These results go back to the Rademacher and Hinchin-Kolmogorov. Sigma n is just a random series, but we regard RK is a step of the simple random walk. Then sigma n can also be a simple random walk with variable step length. And our question is, what happens if we replace the simple random walk with elephant random walk? The elephant random walk is has been introduced by Professor Takei and Professor Roy. The elephant random walk is a discrete time nearest neighbor stochastic process on the integers with a complete memory, introduced by Schütz and Trimper. A formal definition as follows. The first step x1 is plus 1 with probability s, and minus 1 with probability 1 minus s. And let beta n is a family of independent random variables and independent of x1. And also, beta n is uniformly distributed from 1 to n. And for each n, xn plus 1 is defined as x beta n with probability b, and minus x beta n with probability 1 minus b. Then the position of the walker, we denote Tn. And Tn is a partial sum of the xk. We call this beta n memory variables, and p is referred to memory parameter of this elephant random walk. Professor Take introduced asymptotic behavior of this elephant random walk, and we call the phase transition of this elephant random walk. The runtime behavior of this elephant random walk admits a phase transition from diffusive to super diffusive at alpha is equal to 1/2, where alpha is 2p minus 1. And many researchers has proved this limit theorems. If alpha is less than 1/2, then Tn by square root of n converges in distribution to a normal distribution. And we also have lobed iterated logarithm. And if alpha is equal to 1/2, we additional logarithmic term, then this term converges in distribution to a standard normal. And we also have LIN. And the feature of this model, if alpha is greater than 1/2, then Tn by n to the alpha converges almost surely to some random variable L. And moreover, L has a positive variance, and that means L is degenerate, and L is not zero with probability 1. And also, L is not Gaussian, but the fluctuation from L times n alpha is still Gaussian. That means Tn minus L n to the power of alpha by square root of n converges in distribution to this normal distribution. Okay. As the first slide, we introduce elephant random walk with polynomially decaying steps. As an independent case, as the same as independent case, we consider elephant random walks with polynomially decaying steps. Sn is defined as xk. This is the steps of original elephant random walk, and xk divide k to the power gamma and sum of k from 1 to n, where gamma is some positive real. For example, if gamma is greater than 1, then Sn converges almost surely with probability 1, because xk is absolute value 1. The question is whether the runtime behavior of Sn is how influenced memory parameter alpha and step size parameter gamma. And the runtime behavior of Sn and whether it converges or diverges is determined by the critical value gamma c alpha. Gamma c alpha is defined maximum of alpha and 1/2. And precisely, main theorem is for gamma is between 0 and gamma c alpha, an exceptional point, gamma, then Sn diverges with probability 1, and where exceptional point is explicitly a maximum of alpha minus alpha over 1 minus 2 alpha. On the other hand, if gamma is greater than gamma c alpha, then Sn converges with probability 1. This figure illustrates the runtime behavior of elephant random walk with polynomially decaying steps. If alpha is less than 1/2, the convergence criterion is almost the same as independent case. But alpha is greater than 1/2, strong memory effects can shift the critical point for the convergent. This is my first part. And go to the next part. The second part is about the Takagi-van functions and relation and to the elephant random walk, a certain variation of elephant random walks. The Takagi-van functions are defined as follows. D of x is the distance from x to its nearest integer. On the unit interval, dx is this graph. And d of rkx is increasing the frequency to rk on the unit interval. Then fr of x is defined as d rkx and divided rk and infinite sum. This function is called the Takagi-van functions. And fr is a well-known class of continuous, but nowhere differentiable function. F2 is firstly studied Takagi, and F10 is studied by van der Velden independently. We can see the graph of F2 and F3 on the unit interval. The graphical feature of this function heavily depends on the parity of R, this O. And why this is, why appears this feature? We can see from elephant random walk, and this is well understood. Red psi k, d of rkx, and r to the minus k. And we work on the probability space, this probability space with unit interval and with the Borel sigma field and the rubric measure. And psi k plus is right-hand derivative of psi k. And we regard this psi k as a random variables of this probability space. And also the Takagi-van functions is regarded as a random variables of this probability space. This picture is psi 0 and psi 1 for r equals 3. And looking at this picture and nested triangle, we can find the sequence psi k plus satisfies this recursion equation. Psi k plus 1 plus is equal to psi k plus with probability PR and minus psi k plus with probability 1 minus PR. And PR is 1/2 if R is even, and PR is R plus 1 over 2R if R is odd. And we can calculate this psi k, the distribution of psi k plus. Then we can find psi k plus is a stationary Markov chain on this probability space. And psi k plus is plus minus 1 valued. Then these partial sums generate a random walk. The process small sn on this probability space is elephant random walk with parameter PR and memory variable beta n is equivalent n. That means this small Sn almost repeats the very recent past with probability PR. This is pointed by Rajat in 2014, but he called this random walk a correlated random walk. And now we call it this random walk, the elephant random walk, remembering the very recent past. This elephant random walk, for this elephant random walk with remembering the very recent past, we can obtain central limit theorems and row the iterative logarithm. Because Psyche Plus is a Markov chain, and we can use the limit theorems for uniformly mixing sequences. And for example, the start, and we can find these limit theorems, start, installed, and brings way. And S4 Sn is divided by square root of n multiple sigma r. And this term converges in distribution to the standard normal. And all of the iterative logarithm also hold. Sigma r depends on the parity of r. The standard elephant random walk admits the phase transition according to the memory parameter, but remembering the recent past model does not admit phase transition. Also, we consider a weighted version of this elephant random walk, sigma weighted AK, and we call this random walk elephant random walk, remembering the very recent past with variable sequence. The localization criterion is exactly the same as the independent case. That means the weighted sum of elephant random walk converges almost everywhere if and only if AK is square summable. And through these limit theorems for elephant random walk, we can calculate the modulus of continuity of Takagi-van der Velde functions. The increment of FR can be approximated by the elephant random walk in such an equation. The increment is h times elephant random walk at time log r 1 over h and error term. Applying elephant random walk limit theorems for elephant random walk, we can obtain the modulus of continuity of FR. The first one is the central limit theorem type modulus of continuity. And the second one is the law of the iterated logarithm type modulus of continuity. Our result is generalization of Kono and Gamkrelze for R equal to case. And we also consider the generalization version of FR, FRA, and this weighted sum, where AK is satisfies AKA over R to the k minus 1 is absolutely convergent. And as the same as the this elephant random walk with variable step lengths, we can classify the differentiability of FRA by the weighted sequence. That means FRA is differentiable almost everywhere if and only if AK is square summable. And this result also generalization and by Kono and Ferreira-Gomez-Gill and Ferreira-Gomez-Gill Laurent for our two case and even our case. More precisely, if AK is square summable, then FRK is absolutely continuous with respect to the logarithmic measure. Okay, that's all for my talk. Thank you for listening.
Thank you. Questions?
Are these functions that you started off with, this f sub r functions, how do they, is it the classical Noah differentiable construction functions, or are they more than that? Are the functions that you had, this f sub r, right? So, oh yeah, these functions, how did they come up? Like, did they come up only to construct a non-differentiable function everywhere, or something else? Number three, yes.
This.
Because I think the classical, they're due to Steinhaus. I think they were the first ones, and they're not these ones. They're sort of cosines and then more and more frequently summing. So that's what they had. Need not these. I think these come. Do these come from number theory?
This is related to Weierstrass functions and Weierstrass function and related to Fourier series.
They come from Weierstrass. That's even older. Yeah. Okay.
Sure. Yeah. So I was wondering about that term gamma AFC, like that critical point, right? Like, so beyond which it converges and below which it diverges. So
just
yeah. So I was wondering, like, generally, like, what kind of values do we get for a gamma AFC? So yeah, so that thing there, that minus alpha over 1 minus 2 alpha, maximum of alpha and that quantity. Basically, so I wanted to know, like, in like some, let's say, examples, like what does like alpha end up being, like in the let's say the motivating examples for exploring this question, so to speak. Sorry. So I mean, like, we know that parameter is equal to the maximum of alpha minus alpha over 1 minus 2 alpha.
This is
Right. So
this one is right.
Yeah. So, but basically, yeah, I just wanted to know, were there like any like in like the examples you looked at for like when motivating this, like what were like the values of? I guess. Okay.
I'm not sure. So you think that this value minus this value gamma there has a special meaning?
I think this is not special. This is technical expression point.
So it doesn't have a deeper interpretation. Okay. Okay, thank you very much. Tomorrow we meet at 9:30 and dinner starts at 7. Yep, right.